Okay. Good morning, everyone. Yeah, thank you very much to the organizers for giving me the opportunity to present my result. It's always a pleasure to be back in St. Petersburg. So I will discuss various of my recent projects which were connected actually with the radius of neutron stars. So we had a very nice introduction in the previous talk, but I will just set the framework of the problem. So one of the mystery of neutron stars is the equation of state, because as was mentioned before, so neutron star matter is a many-body system of strongly interacting particles at 0 temperature, and we don't have at the moment a solution. So an equation of state basically describes the properties and the composition of neutron star matter, and it can be roughly, it can be written as a relation between the pressure and the density, and which is exactly what I show here. And then the game we play with neutron stars is when we choose an equation of state. We solve the Tolman-Oppenheimer-Volkoff equation for hydrostatic equilibrium in general relativity, and then we obtain some relation between the mass and the radius, and the game is to try to obtain some astrophysical constraint on the mass and the radius to constrain the equation of state. And at the moment, the only constraint we have, which is widely accepted, is this constraint of 2 solar masses. Okay, so but in the next few years, there will be a set of missions which aim at measuring the radii of neutron star. And this is a topic we focused on at Copernicus Center with my collaborators. And there is actually a tricky point, because if you have a look at the neutron star structure, the core of a neutron star is made of an homogeneous mixture of baryons. And so it's quite simple to calculate an equation of state for the core. An equation of state for the crust is more tricky to calculate, because the crust is formed of a lattice of nuclei. So it's non-uniform. So the consequence is you have many equations of state for the core of neutron stars and not so many for the crust of neutron stars. And in particular, you have very few unified equations of state. Unified in the sense, as was mentioned in the previous talk, that the same nuclear interaction is used to calculate the core and the crust equation of state. So what people usually do, and what I also did, is to take an equation of state for the crust, an equation of state for the core, and then you try to connect them. So this is an example here. So imagine that you want to build an equation of state based on the NL3. So one model, this blue line, an equation of state based on this NL3 model for the core. If you don't have a model for the crust, well, what you have to do is to choose an equation of state for the crust and then to connect them. And so this is what is plotted here. And so in this work here, what we did is we had a look at various methods in the literature that were used to connect core and crust. And for each of these methods, we calculated the mass-radius relation and the relation between the mass and the thickness of the crust. And what we saw is that just due to the way you connect the core and the crust, you can introduce an uncertainty on the radius which is up to a few percent. This is not an observational uncertainty. This is purely theoretical uncertainty, which is due to the way you connect the core and the crust. And this is actually quite worrying in the sense that the next generation of X-ray telescopes, so for example NICER, Athena or LOFT, are supposed to measure the radii with an uncertainty which is similar. So you have really to tackle this problem, to solve this problem. And so one way to solve this problem, which was mentioned before in the previous talk, and which I also mentioned before, is to use unified equations of state, in the sense that the core and the crust are calculated with the same nuclear interaction. And so there were very few such equations of state. So I can think of this Dusha and Hensel, also the equations of state by Nicolas Chavel and collaborators, and this Sharma equation of state, which was mentioned. So what I did with my collaborators, this long list of people here, is to calculate a large set of unified equations of state, so 33 nucleonic equations of state, all consistent with 2 solar masses. So belonging to 2 classes of equations of state, SCRM equations of state and relativistic mean field ones, and also 15 hyperonic equations of state for relativistic mean field models. And the tables for all those equations of state are available as a supplemental material to the paper, and they should be soon available on the Compose database. We also confronted our large set of equations of state to a set of constraints. So first, experimental constraints on the symmetry energy and its slope. So constraint obtained using different experimental observables. So they are listed here, and they correspond to this different set of contours. And the region where all constraints meet is this white region. And we also confronted our models to theoretical calculation that were mentioned in the previous talk. So, so typically this scalar effective field theory and this quantum Monte Carlo technique. And so we end up with a set of 4 different models. So 1 SCRM and 3 RMF, which are consistent with our set of constraints. And we also, for these models, we also have 4 hyperonic equations of state consistent with the constraints. Another way, so that was one way to tackle the problem of the core cross connection, that is having a unified equation of state. But this is not always the case. So what we did with my colleague at Copernicus Center is to develop an approximate approach for the crust of a neutron star. So the idea is to take a shell in the crust of a neutron star located between 2 pressures, say P1, P2. And then a good approximation consists in saying that the mass of this shell is small compared to the total mass of the neutron star, and then you can obtain basically the Tov equation simplifies to this equation. And then you can integrate this equation, and you obtain this relation here between the radii at the top and bottom of the shell as a function of the chemical potential at the top and bottom of the shell. Now, this approximation, this formula is valid if you don't have any jump in the chemical potential. This will be of importance in few slides. Now, what you can do is you extend your shell to the total, to the whole crust of the neutron star, and then you end up with such a relation here, which connects the radius of the core to the total radius of the star as a function of the chemical potential at the surface, which is basically known, and the chemical potential at the core crust interface, so here. And this is the subtle thing in our approach, but I will develop this in 2 slides. And so basically with our approach, what you only need to do is to take an equation of state for the core, which you decide to stop at a density. And again, this is the tricky part I will develop in the next slide. Then you solve the equation, the Tolman-Oppenheimer-Volkoff equation for the core. So you obtain a relation, so those are the blue lines, between the radius of the core and the mass. And then using this simple formula here, you obtain the relation between the total radius of the star as a function, the mass as a function of the total radius of the star. So those are the red lines. And the black lines here are unified equations of state. And you see that with this approach, actually, you obtain estimates of the radii, which are with a very good approximation, with an uncertainty of few tenths of %, and for the crust thickness of less than 1%. So with this approach, you don't need an equation of state for the crust, which is actually fairly complicated to calculate. You just need an equation of state for the core. But so as I mentioned twice already, the tricky part in the game in this approach is to calculate where to stop the equation of state for the core. And so we had a look at a large set of equations of state. And basically for actually a large range of value of the slope of the symmetry energy, the core crust transition is usually located within this range. So a good value for the core crust transition in our approach, a good prescription is to take half saturation density. So with this approach here, taking this value of the core crust transition, basically you can obtain the relation between the total mass of the total radius of the star and the mass of the star just using the core equation of state with a very good approximation. We played a similar game for neutron star with an accreted crust. What is different for neutron star with an accreted crust is that so an accreted crust is not composed of catalyzed matter, and so you have jumps in the chemical potential. Each jump corresponds to an energy source. And so basically you play the same game as the one we played before, except that this time you consider a series of shells between two heat sources, between two jumps in the chemical potential. And so you end up with a relation here which connects the radius of the core to the total radius of the star as a function, again, of the chemical potential at the core crust transition, at the surface, and this Q dot here, which corresponds to the total heat release, so the sum of these different density jumps. And with this approach, I don't enter into details because I don't have much time, you basically obtain a simple relation which connects the radius of a neutron star with an accreted crust to the radius of a neutron star with a catalyzed crust as a function of the total heat release for a neutron star with an accreted crust. And so this is also a simple approximation, simple formula. Okay, now I will quickly mention hyperons and hyperonic equations of state. So as a reminder, so hyperons are baryons, so as neutrons and protons, except that they contain at least one strange quark. So they are, few here are listed by order of increasing mass. And so some models predict that there might be hyperons at the very center of neutron stars. And so what I plot here is for a given model is in black the equation of state without hyperons, so the nucleonic equation of state, and in blue with hyperons. And so if you play the game of calculating the TOV solution, basically you end up with the following mass-reduce relation, and you see that the fact that including hyperons decreases the pressure at high density result in a decrease of the maximum mass. So this is why when two solar mass neutron stars were measured, some people claim that actually hyperons are ruled out, and this is the I must point out that here the hyperonic equation of state, so the blue one, is ruled out, but I chose that model here on purpose for say pedagogical purposes. So the so-called Hyperon Puzzle tried to answer to the question whether it's possible to have hyperons in two solar masses, hyperons in neutron stars, and yet to have two solar mass, maximum mass larger than two solar mass. And in a paper a couple of years ago with my collaborators at Copernicus Center, what we did is we had a look at all the equations of state for hyperonic matter that were consistent with two solar masses at the time of the publication, and we found out that basically the problem that all of them had is that in order to be consistent with two solar masses, they had to compensate for the decrease of the pressure at high density by making the pressure much larger at low density. And this very large pressure at low density was actually inconsistent with calculations that were mentioned in the previous talk and that I mentioned before. So calculation, for example, using chiral effective field theory. And so since this paper, which pointed out the problem, there were some works which managed to build equations of state consistent with two solar masses and consistent with not too high pressure at low density. So we typically obtain some in this work, and I should also mention the work by Michaela Hörtel and collaborators, among others. Okay, and so while we were working on building such hyperonic equations of state consistent with two solar masses, one of our colleagues, so Isa Gvidania, pointed out that the way we, and actually everyone include hyperons in neutron star is was likely inconsistent with the available experimental data on hypernuclei. So in hypernuclei is a nuclei except is like a nuclei, so neutrons and protons, with in addition at least one hyperons. And they are observed in laboratory and their properties are measured since the 1950s. And at the moment, so the properties of something like 40 lambda hypernuclei have been measured in laboratory. It has been possible to observe Xi hypernuclei in laboratories, but their properties are not well determined. And so far, no sigma hypernuclei were observed in laboratories, suggesting that potentially they could not exist, meaning that the interaction between the sigma and the nucleon could be repulsive. And so far, there is only one unambiguous measurement of the properties of a double lambda hypernuclei. So this is this one here, this double lambda helium. So two neutrons, 2 protons, and 2 lambdas. And so the usual way of included hyperons in relativistic mean field models is by adjusting the coupling, for example, for the lambda, to reproduce 2 quantities. This quantity here, the lambda potential in symmetric nuclear matter, and this other quantity is the lambda potential in pure lambda matter. And those are the values that are usually taken, and they are actually interpretation of the experimental data. And what we did with my collaborators is we tried this time not to adjust the coupling to reproduce these quantity, which are interpreting the experimental data, but really to adjust the coupling, the properties, to real experimental data. So we did model hypernuclei, and so we, for example, adjust the data to reproduce the properties of lambda hypernuclei. And if we do this, once we calibrated our model to reproduce the experimental data, we could calculate this quantity here, which is usually used. And we saw that in absolute value, the value that we have are actually higher than the usual value taken in the literature. And we did the same, this time adjusting the coupling to double lambda hypernuclei, and similarly we obtained values of this quantity here, which are in absolute value larger. So the way hypernuclei lambdas were included in models were actually indeed inconsistent with the data. So our next game was to include the other hyperons. I won't enter into the details, but we try to take into account the uncertainty we have on these, because again, we don't have basically constraint on them. And we built Hyperonic equations of state, and we confronted them to two solar mass, the existence of two solar mass neutron stars. And basically what we saw is that all of our models were consistent with two solar masses. So it means this is actually not only due to the uncertainty on the Hyperon properties, but also due to, mostly due to the uncertainty on the nucleonic equation of state. So at the moment, there is no solution to the Hyperon puzzle. It's due to the uncertainty on the nucleonic equation of state and on the Hyperonic equation of state. It's possible to build to have two solar mass neutron stars with hyperons. And I will quickly mention also one way of potentially constraining the radius of neutron star is by noticing that there are correlations between nuclear parameters and the radius of neutron star. For example, between the slope of the symmetry energy and the radius. So this was pointed out in these works. And so in this paper here, we played the game of using a large set of equations of state, and we find that indeed there are correlations between the radius and the slope of the symmetry energy. And what is interesting is that this slope here could be potentially measured in the next few years in laboratories, thanks to the measurement of neutron skin thickness. And you can also play a similar game by noticing that there is also a correlation between the radius of a neutron star and linear correlation, a linear combination of the slope of the symmetry energy and of the incompressibility. This is what is plotted here. Okay, we don't see too well the gray strip here, but this gray strip here corresponds to an experimental constraint, and so potentially by measuring the slope of the incompressibility, you can obtain a constraint on the radius of neutron star. So I will just quickly summarize. So what I really want to point out is that one has to be careful when connecting an equation of state for the core and for the crust. Otherwise, you introduce some uncertainty, which can be as large as the uncertainty you would obtain from observations. So there are a few ways of tackling this problem. One is to use unified equations of state. And if your favorite unified equations of state doesn't have, I mean, if an equation of state for the crust is not available for your favorite equation of state, basically you can use the approximate formula that I mentioned. And it's possible to have, at the moment, two solar masses in neutron star with hyperons because of uncertainty on the in the hyperonic sector and in the nucleonic sector. Thank you.
Thank you. We have time for 2 questions, please.
So thank you for this very nice talk. So you know there's some astrophysical radius constraints, and so I'm in particular thinking about this recent very nice paper by Nathalie et al., where they combine some observations with some quantum Monte Carlo model, and they find lower radii than a lot of the things you've been showing. So I wanted to, if you could comment on this a little bit.
So yeah, so let's say that they find radii like smaller, let's say 12 kilometers, right? I mean, and okay, here we are sort of marginally consistent, but I think actually this, I mean, this approach will be presented, this work will be presented later this week. But I believe that there are, at the moment, no consensus on the technique, and also there are observational uncertainties regarding the modeling of the phenomena itself. So I would personally take this constraint with a, yeah, with a grain of salt. But yeah, and well, I don't know.
One more question, please.
You said that your new equation of state passes well the constraints from chiral effective field theory at low densities, right?
Mm-hmm.
So, and what about the flow constraint of Danielewicz for the pressure in the isospin symmetric matter, which follows from analysis of flows and heavy ion collisions?
So so those are those equations of state. We decided actually not to use this constraint on the flow, arguing that the way it was obtained is really model dependent, and what would be necessary is, is to redo the calculation that had been done using a large set of equations of state. So we decided to disregard it. But as far as I can remember, some of those actually are consistent with the flow. But this has to be double-checked. I can double-check for you.
Mm-hmm. Okay, thank you.
Let us speak, Marlon.